Okay, so we have discussed quantization of free electromagnetic field as well as quantization of the Dirac field. What we will see from now on is the interaction between the Dirac field and the electromagnetic field. So, the interaction is introduced, the minimal interaction is introduced in the following manner. You consider the Dirac Lagrangian which is given by LD equal to psi bar I gamma mu del mu minus m psi. Now, notice that this is a global U1 invariance. So, if you make psi of x to transfer as e to the power I e alpha psi of x, where e and alpha are constants, then this Lagrangian density is invariant under this transformation. Now, the question is, if we want to make this global U1 to a local U1, then what we would do? We would make this alpha to be actually a function of x, space time coordinates. Okay. Of course, if alpha is x dependent, then this Lagrangian is no longer invariant under this U1 transformation. What you would do is you would modify this Lagrangian in such a way that it is invariant under U1 transformation. How do you modify this? You just change this del mu, the partial derivative, to covariant derivative. So, del mu goes to d mu, which is del mu minus I e a mu, where a mu is the gauge field, which transforms under gauge transformation like a mu goes to a mu plus del mu alpha. Then this Lagrangian density, which I will call as L, which is given by psi bar I gamma mu d mu minus m psi. This is going to be invariant under the local gauge transformation. So, if we would like to incorporate the dynamics of the gauge field as well, then we will add to this the Maxwell's Lagrangian, which is given by minus 1/4 f mu nu f mu nu. So, as a result we get the Lagrangian density, which actually contains the free Dirac Lagrangian, the free Maxwell's Lagrangian, and the interaction between them. Where L Dirac is given by this, L Maxwell is this quantity here 1/4 f mu nu, and what is L interact? The interacting part of the Lagrangian is determined from this term here, and this is given by psi bar I gamma mu times minus I e a mu psi. Okay. So, L interacting has this form. Let me use the convention where yeah, okay, that is fine. So, this is E times psi bar gamma mu a mu psi, or in other words E psi bar a slash psi. This is the interacting part of the Lagrangian density, and we will see what do we get when we take this theory and quantize it. This is one of the most important Lagrangian density that you will come across in physics. It describes a wide range of physical processes. Some of the simplest ones are the Compton scattering, where your photon interacts with electron, gamma plus E minus, or it can also describe electron scattering, electron going to electron. It can also describe electron positron scattering, E plus E minus going to E plus E minus, and pair creation in the sense gamma plus gamma going to E plus E minus, or pair annihilation, which is E plus E minus going to E plus gamma, and a number of other physical processes. We will discuss some of them, and then we will compute the cross section for that. But before that, we need to to consider any of these physical processes, what we need to know is what is the S matrix, and then what are its elements, what are the which terms in the S matrix contribute to what physical processes, and all those things that we need to know. Or in other words, we can derive a set of very simple rules, which are the Feynman rules, which will tell us how to compute the amplitude for any physical process. What we will do is, we will first consider the S matrix, and then from the S matrix we will derive the Feynman rules. Okay. So of course, the interacting Hamiltonian density, which I will call as Hi, is minus of this. So minus E psi bar A slash psi, and the S matrix is given by time order product of e to the power minus I integration of d4x L psi of x. I can evaluate it order by order. So this is nothing but time order product of sum over n equal to 0 to infinity minus I to the power n divided by n factorial d4x1 up to d4xn and Si of x1, so on up to Si of xn. Right. So I will denote them as sum over n equal to 0 to infinity Sn, where n equal to 0 correspond to the first term in this expansion, n equal to 1 is the second term, and so on. So what is S0? S0 of course is identity, and it just gives us the forward scattering part. So we will forget about S0, and then we can consider the other terms. So let us look at the second term in the expansion, which I will call as the first order term, because it is linear in E, and the second term in the expansion, which is quadratic in E, which I will call as the second order term. So, the first order term is S1, I will call according to my notation. S1 is given by minus I integration d4x time order product of E times psi bar A slash psi. Okay, we will discuss more about this term in a moment, but let's look at the second term in the expansion. So, S2 is given by minus IE square divided by 2 factorial d4x1 d4x2 and time order product of psi bar of x1 A slash x1 psi of x1 and then psi bar x2 A slash x2 psi of x2. Now, we can use Wick's theorem to express this time order product in terms of normal ordered products. So, what we will get when we express it in terms of the normal order product? We will of course get first term as the normal order product of this, then all one contraction terms. So, what are all one contraction terms? This psi x1 can contract with psi bar x2, A x1 can contract with A x2 and psi bar x1 can contract with psi of x2. So, these are all one contraction term. Then you can have two contraction terms. What are the two contraction terms? This pair and this pair can contract or so on. Okay. So, there are, and then finally you will have three contraction terms. There will be one such terms. So, let us write down these quantities. I will denote them as S21 and so on with a subscript which basically gives us various terms in the Wick expansion d4x1, d4x2 and then normal order product of psi bar x1 A slash of x1 psi x1 psi bar x2 A slash x2 psi x2. Now, this does not involve any contractions. Now, we will consider the one contraction term. So, S22 I will call, S22 is minus I square over 2 factorial and integration d4x1 d4x2. So, there are three contractions, but out of which one involves the contraction of Ax1 with Ax2, the other two terms involve contraction of the fermions. So, I will group the contraction of fermions into one term and then the contraction of the gauge fields I will write it in a separate term. So, this is normal order product of psi bar x1 A slash x1 psi x1 psi bar x2 A slash x2 psi x2, where this contracts with this and then normal order product of psi bar of x1 A slash x1 psi x1 psi bar x2 a slash x2 psi x2, where this psi bar of x1 contracts with this. Okay. So, and finally, S2 3, which involves the contraction of A x1 with A x2. So, this is minus I e square over 2 factorial integration normal order product of psi bar x1 gamma alpha A alpha of x1 psi x1 psi bar of x2 gamma beta A beta of x2 psi of x2, where A alpha x1 contracts with A beta x2. This contains all 1 contraction terms. Now, we will look at all the 2 contraction terms. So, what are all 2 contraction terms? I will denote S2 4 as the one which contains contraction of a pair of A of x1 and A x2 and psi bar. Okay. So, it involves one pair from the gauge field and one pair from the fermion field. Therefore, this is minus I e square over 2 factorial d4 x1 d4 x2 normal order product of psi bar x1 gamma alpha A alpha x1 psi x1 psi bar x2 gamma beta A beta psi of x2, where psi x1 contracts with psi bar x1 and A alpha of x1 contracts with A beta of x2, and then I can have similarly normal order product of psi bar x1 gamma alpha A alpha of x1 psi x1 psi bar x2 gamma beta A beta x2 psi of x2, where A alpha x1 contracts with A beta of x2 and psi bar x1 contracts with psi of x2. Now, I have one more term involving 2 contraction terms which will contract both the pairs of fermions. So, S25 is minus I e square over 2 factorial normal order product of where this contracts with this, and then this one contracts with this. And finally, the last term which involves all three contraction terms. Where this contracts with this, A alpha x1 contracts with A beta x2 and this. So this is the list of all second order terms. We can go on like this, but we will stop with second order and then we will see whether we can we can find a simpler way to compute the amplitudes for a physical process at any given order. So let us look at now each of these terms. Let us look at the first order term here, the first order term, and then what kind of physical processes to which it can contribute. Okay. So S1 which is also equal to normal order product of itself minus I d4 x1 d4x normal order product of psi bar of x1 gamma alpha A alpha of x1 psi of x1. So this is the only term in the weak expansion. Now, what is the psi bar of x, psi of x and so on? We know psi of x is the mode expansion integration dqk over 2 pi q m over k0 sum over s equal to 1 to cs of k u s of k e to the power minus I k dot x plus ds dagger k Vsk e to the power I k dot x, and psi bar of x is d cube k over 2 pi cube m over k0 sum over s cs dagger us bar k e to the power I k dot x plus ds k vs bar of k e to the power minus I k dot x. Similarly, we have a mu of x for which the mode expansion is given by dqk over to pi cube to k 0 sum over lambda equal to 0 to 3 a lambda k epsilon lambda mu k e to the power minus I k dot x plus a lambda dagger k epsilon mu lambda star k e to the power I k dot x. So, what are these? What do these terms represent? This I will write it as psi plus and psi minus, okay, where this I will call as psi plus of x, this term I will call as psi minus of x. So, psi minus of x contains the annihilation operator for one electron. Sorry, psi minus I will denote it as annihilation. Yeah, okay. This is the creation part. So, this I will denote as psi. This I will denote as psi minus, this I will denote as psi plus of x, because this is the positive frequency part and this is the negative frequency part. This operator actually is a creation operator for an electron. Okay. This d dagger field is so as I said, Cs are the positively charged particle. These Cs daggers create positively charged particle, whereas the ds daggers actually creates negatively charged particle. Therefore, this psi minus of x, I will denote this as the creation operator for an electron, whereas this psi plus of x is, it will describe the annihilation of a positron. Okay. So, when I write psi of x, psi of x is psi plus of x plus psi minus of x, this will create an electron at the space time point x, whereas this will annihilate a positron at x. On the other hand, psi bar of x, I will write it as psi bar minus of x, and this term here I will write it as psi bar plus of x. So, psi bar minus of x creates an electron, whereas this annihilates a positron. So, psi bar minus of x plus psi bar plus of x, this one psi bar minus creates a positron, psi bar plus annihilates an electron. Okay. So, here this the negative frequency component actually creates an electron, whereas the positive frequency component annihilates a positron. Here the opposite thing happens, in the sense that the positive frequency component here creates a positron, whereas the negative frequency component creates a positron, whereas the positive frequency component annihilates an electron. What about this? Here the A mu, the first term, which I will call as A mu plus, and this term I will call as A mu minus. So, this one annihilates a photon, whereas this one creates a photon. Okay. So, now what kind of terms are there in the first order term in the S matrix? Let us look at it. So, S1 minus IE d4 x normal order product of psi bar of x gamma mu A mu of x psi of x. Okay. So, what kind of physical processes are there to which this term will contribute, contribute in a non-trivial way, in the sense that it will give a non-zero contribution. This psi bar of x has two terms, psi bar plus psi bar minus. Similarly, A mu has A mu plus A mu minus, and psi of x has psi plus psi minus. So, a typical term, of course, you can list all the terms, but typically it will have terms which are of this type: normal order product of psi bar minus gamma mu A mu plus of x psi bar minus of x, let us say psi plus of x. Consider a typical term which looks like this. So, here this psi plus of x, you just look at this, it annihilates a positron at x. So, you consider a positron which is annihilated at this point x. So, this I will denote it as a positron E plus. I will use a different notation little later, but for the time being it is, and then A mu plus annihilates a photon at x. So, a photon is annihilated here. So, you have an E plus, which there is an incoming positron, there is an incoming photon, and then psi plus of x denotes psi bar minus, which basically denotes creation of a electron, right? Psi bar minus is creation of a positron. So, a positron is created again at this space time point x, right. So, psi plus annihilation of a positron, psi bar minus, good. So, this is what is the physical process to which a term like this will give a non-zero contribution. We will see little later that in fact if we work out the amplitude, then the amplitude actually vanishes, but just looking at the term in the S matrix, you can say that this is what is the process. So, if you have an in state which is basically a positron and a photon, and if you have a out state which is one positron, then this is the term in the S matrix which might give a physical non-zero amplitude. Okay, so similarly there will be other terms here which will describe other physical processes, but we will see little later that all such terms actually at this order, all the terms gives 0 contribution to any physical amplitude that you can consider. So this term does not give anything interesting. Now we can look at the second order term. Let us consider a typical second order term. Which is S22. Okay. You will see, you can convince yourself that S21 also does not give contribution to any physical process. S22 is the first non-trivial term which actually gives contribution to many physical processes. We will see what are the physical processes to which this term gives non-trivial contributions, and then in what way it gives contribution to physical processes. So S22 according to our notation is minus E square over 2 factorial d4 x1 d4 x2 and then normal order product of psi bar x1 slash x1 psi of x1 psi bar x2 slash x2 psi of x2, where this is contracted with this, and then psi bar x1 slash of x1 psi of x1 psi bar x2 slash x2 psi of x2. All right, this is contracted with this. We can we simplify this term? Of course, we can simplify it a bit. You notice that these three terms contains two fermion operator and one boson operator. Okay, so you can move it freely inside the normal ordering without any change of sign. What I will do is that I will take all these three operators to the beginning here. So the second term here is normal order product of psi bar x2 a slash of x2 psi x2 psi bar x1 a slash of x1 psi of x1. If it had contained odd number of fermions, then you may or may not have changed sign. Okay. So now look at this. So which term is contracted with what? Psi bar x1 is contracted with psi of x2. So this is contracted with this here. But now since x2 is a dummy variable, it is integrated over x1 and x2. You can change this variable x2 to x1 and x1 to x2, then you can see that this term is nothing but it is identical to the first term. So you can write S2 as minus E square, and the second term here is removed. So what are the physical processes to which this can give non-vanishing contributions? Again, so you can look at psi bar in terms of psi bar plus, psi bar minus, and so on. So you can see that it will of course gamma plus E minus going to gamma plus E minus. It can give non-zero contribution to the Compton scattering, okay, because it can. So, first of all, this there is a propagator here, okay. This term psi of x1, psi bar of x2, this tells you the propagation of an electron from x1 to x2, whereas here this psi bar x1 can contain psi bar plus psi bar minus. What is psi bar minus describing? Psi bar minus is describing creation of a positron. Psi bar minus annihilation of an initial electron. Okay. So, you can have a process like this. Similarly, you can psi of x will contain psi what I will use is the following. I will, when we consider the mode expansion for psi, psi contains a bunch of terms, and then we have already seen C of k u k of x e to the power minus I k dot x plus d dagger k v k e to the power I k dot x, right? dq k over 2 pi q m over k0 and sum over s here cs us ds vs. So, I will denote these C's and C daggers to be the creation and annihilation of an electron, okay. So, operators, whereas D's and D daggers I will denote them as creation and annihilation operators for E plus positron, okay. And I will consistently follow this notation throughout the course of our lecture. So, then what happens is, here the first term here is psi plus. So, psi plus describes the annihilation of an electron, not positron. So, psi bar of x is psi bar plus of x plus psi bar minus of x, whereas psi plus of x, which contains Cs, is describing annihilation of an electron, whereas psi minus of x describes the creation of a positron at x of at x, whereas psi bar plus of x describes annihilation of a positron at x, and psi bar minus of x describes creation of an electron at x. Okay. So, this is the notation that we will be using throughout. Now, so there are of course this physical process is there. You can also have psi bar plus of x 1, and you can have psi plus of x 2, a mu plus of x 1, a nu plus of x 2. It may contain these, I mean one such term will contain all these fields here, right. So, what physical process this will describe? What is psi bar plus of x 1? Annihilation of an electron, annihilation of a positron at x 1. So, you have a positron, this is let us say x 1, an incoming positron is there which is annihilated. What about psi bar plus of x 2? It creates a positron. Psi plus creates annihilation of an electron. So, it's there is an incoming electron which it's annihilation of an electron at x 2. So, you have x 2, and this describes the annihilation of a photon at x 1. This describes an annihilation of a photon at x 2, right. So, there is an incoming photon here, this is gamma. So, there will be some such process like that which will I don't know what kind of process is. If there is a psi minus, of course, it will create an electron, but it will not conserve charge. Okay. Psi minus creates a positron. Okay. So, then this will of course describe something like a positron electron scattering. There are other, so what I suggest is you look at all the terms, you write psi bar in terms of psi bar plus, psi bar minus, and so on, and these are the physical processes which will be described in gamma plus E minus going to gamma plus E minus, and it will also describe a pair creation gamma gamma going to E plus plus E minus, and pair annihilation which is E plus plus E minus going to gamma gamma. So, what we were struggling to see is whether E plus plus E minus going to E plus plus E minus, something like that, or whether E minus plus E minus going to E minus plus E minus. You can see, you can convince yourself that processes like this will not be described by this term in the S matrix. Okay. So, these are the physical processes which will be described by this, and then in the next lecture we will see how can we describe these physical processes, and we will see if there is a simpler way to, if we have a set of rules which will tell us how to, instead of looking at these terms each and every time, if we can directly compute the matrix elements for any physical process. All right.